Hey, what's going on, guys? Let's look at this problem right here. Here this question is asking a MOSFET in saturation has a drain current of 1 milliampere for VDS is equal to 0.5 voltage. If the channel length modulation coefficient is 0.05 voltage minus 1, the output resistance in kilo ohm of the MOSFET is what? Okay, here the question is asking us to find out the output resistance. Now let's look at the MOSFET diagram. Let's go ahead and see what's going to be the output resistance of a MOSFET. So if you look at a MOSFET diagram like this, okay, let's draw a sample MOSFET diagram. Okay, let's say we have a MOSFET here, and for a MOSFET, you know that this is the drain and this is the gate and this is the source. Okay, now here we will have a drain current, but output resistance is nothing but the output, like resistance across the output terminals. Now if you consider MOSFET, for a MOSFET this drain is the output terminal and S source is the common terminal and G is the input. This is the gate is the input. Okay, now output resistance, how can we calculate the output resistance? That's going to be just voltage across the output terminals. That's nothing but VD minus VS. Okay, so VD minus voltage across the drain minus voltage across the source. So VD minus VS divided by the current. So this is drain current. Okay, so ID. This is going to give us the output resistance, but this is for static resistance. So if you want to calculate the dynamic resistance, you can put, instead of writing VD minus VS, we can write VDS. Okay, VDS. So this is for static resistance, but if you want to calculate dynamic resistance, you have to differentiate this one. So you have to put dou OD. So dou VDS divided by dou ID. So this is the equation we have to find out we have to use in order to find out the dynamic output resistance. Now here we are going to calculate the dynamic output resistance. That's the question. Now if you look at this one, let's look at the condition here. Here we have the MOSFET in saturation and also it's going through channel length modulation effect. Okay, so when we have this condition, the drain current equation is going to be this one. But before I go and write that one, let's mention this one. So when we have with channel length modulation effect, so CLM, the ID equation, drain current equation is going to be equivalent to, so it's saturation and channel length modulation effect. So in that condition, the drain current equation is going to be beta times VGS minus VT whole square times 1 plus lambda ds. Okay, lambda VDS, lambda VDS. So this is the equation for the drain current. Now here we are interested in finding this one, R output. So in order to derive this equation, we have to have some formula like this. We have to have partial derivative of VDS with respect to ID, or derivative of ID with respect to VDS, and then we can flip around. For this one, if you look at this one, this is a current equation. So if I take derivative with respect to VDS, that is reciprocal of this one, right? So after we find the final answer, we can just flip it around. Like we can find the reciprocal of that one. That's going to be the resistance, output resistance. Okay, now let's go ahead and take the partial derivative of this one. So here we have to differentiate both sides with respect to, here you can see with respect to VDS, because that's the reciprocal of this one. So with respect to VDS, if we do that, what's going to happen? Here you can see we are multiplying this whole term with this 1 and this lambda VDS. But for when you multiply this one with 1, do we have any VDS in this one? We don't have anything, right? We don't have any VDS. So partial derivative of ID with respect to VDS. So when we do that, this is going to be treated as a constant because we are only taking the derivative with respect to VDS. So wherever we have VDS, then only we will take the derivative, otherwise it's going to be 0, otherwise the thing is going to be constant. So for the first term it's going to be constant, okay? So the whole term is going to be 0. And if you look at the second term, we have lambda VDS. If you multiply the whole thing, this VDS will become 1, right? So which if you differentiate with this one with respect to VDS, this will become 1, and the others are going to be constant, so that's remain. So lambda times the whole term. So this is going to give us 0 plus, let's avoid the bracket, 0 plus the whole term, beta VGS minus VT square times lambda. Okay, so this is the one we are having right now. Now if you look at this equation, so if we take when this equation, when lambda is equal to 0, so if you put 0 for lambda, this is the only thing that's going to remain, right? So we can write that one in somewhere here, because we are going to use that situation. So when ID is going to be equal to only this term, when lambda is equal to 0, so ID is going to be equal to beta times VGS minus VT whole square when lambda is equal to 0, when lambda is equal to 0. So this one is going to be useful because we can replace this whole term here with ID, right? With ID, because if you look at this one, ID is equal to beta times VGS minus VT whole square when lambda is equal to 0. So we can rewrite this equation here as ID times lambda. Okay. Now ID times lambda, this is partial derivative of ID with respect to VDS. But if you look at this one, here what we have, output resistance equal to partial derivative of VDS with respect to ID. Here we have ID with respect to VDS. So if you flip around, that's going to be the RO. So this is equal to 1 over RO. Therefore RO is going to be what? 1 over this term, right? 1 over ID lambda. Now let's look at the values given. We have the drain current provided, 1 milliampere, that's ID. And we have the channel length modulation effect. So this is channel length modulation effect coefficient, that's lambda. So here we have that one provided, that's 0.05, that's the lambda. Okay, so this is going to be what we are going to have, 1 over 1 milliampere times 0.05 voltage minus 1, and that's going to give us the resistance. And if you calculate this one, since we have milli, that's going to make this whole thing kilo, and if you divide 1 by 0.05, that's going to give you 20. So 20 kilo ohm is the resistance, output resistance, and this is dynamic output resistance because we are differentiating VDS over ID. So this is going to be 20 kilo ohm resistance, and that's our final answer. I hope this helps. Thanks for watching.